Hello and welcome to my little presentation. I'm Marco, a PhD student from Magdeburg, and I'm going to talk about a RISE project, programming a geometric realization of non-affine Coxeter groups that I did together with an intern summer 2020. As a little teaser, first of all, this picture. This is one of the end products of this project. And before I'm going to explain you this picture, I shortly tell you what the RISE project is. So it's a DAAD-funded internship, and yeah, I had Mireia Taus and I here in Magdeburg as an intern. She's a graduate student at the University of Warwick, and yeah, we did everything I present to you together. The basis of this project are the Python packages drawSvg and hyperbolic by Casey Duckering, and Sage Math, that's an algebra computer system based on Python. Okay, the pictures that we created, they have two layers, and the first layer basically is the hyperbolic, the two-dimensional hyperbolic space in the Poincaré disk model. We have hyperplanes in this model and tessellations of the hyperbolic space into two-dimensional simplices, with the conditions that the angles of the simplices are integer fractions of pi, and reflecting on the sides of one simplex generates the whole tessellation just like this. So this is a full tessellation. That's the first layer. Now we come to the second layer, hopefully. The second layer visualizes the following problem. So we fix a tile in black, and then for every other tile we ask ourselves, what is the minimal number of hyperplane reflections to reflect back to the black tile? So now you see a gray tile, and if we reflect on this hyperplane, we get a bit more darker gray tile. Reflect on the second red hyperplane, we go to this tile, and the third reflection reflects the tile back to the black tile. I have not given any proof that this is really minimal, but you have to trust me that it is. If we do this for every tile, we get this kind of patterns. And okay, what is the mathematical background? You can basically see it as a Coxeter complex of non-affine Coxeter groups, infinite non-affine Coxeter groups, if you want. This is the definition of a Coxeter system. So the gray conditions above are exactly the conditions from the simplices. And yeah, they translate to this definition. We have a finite generating system. Reflections are self-inverse. And here, I hope you see my cursor. These are called braid relations. Okay, what is a Coxeter complex? I also want to show you the definition of a Coxeter complex. The most important thing of this, maybe at first glance a bit complex definition, is that we have for every group element, we have a tile, a simplex that is associated to the group element, and we glue these tiles together in a way that respects the braid relations, basically. That's what I want to tell you about the Coxeter complex. And then we also have an abstract definition of reflection length. So a reflection is a conjugate of a generator, and yeah, analogously to the word length, you can define reflection length. Below you see some examples. If you want to stop the video and maybe go through the example, you're welcome. And lastly, I want to show you some pictures and yeah, tell you that in fact there's nothing much known about reflection length, though not much known about reflection length in hyperbolic Coxeter groups, except that the reflection length is unbounded. And as far as I know, we are the first ones who visualize reflection length in infinite non-affine Coxeter groups. So thanks a lot, and I'm looking forward to your questions.